Hello everyone, my name is Logan and welcome back to the lecture hall. Today we're covering section 2.4 of our UCI Math 2A course, the precise definition of a limit. So if you remember back to 2.2 with the intuitive definition of a limit, we see x is close to a and f of x gets closer and closer to L. And the statements are too vague and we need a better definition in order to give us the real definition of a limit. So, I'm going to show you the definition of a limit, but we're not going to have to prove it or do any of that because that's what you do in Math 140A, so we'll get there when we get there. So, here it is. The precise definition of a limit. The limit, as x approaches a of f of x, is equal to L if, so then there's this like upside down a, that means for every, for every epsilon is just like a random number, it can be really anything. For every epsilon greater than 0, this backwards e, this means there exists a delta greater than 0 such that St if x minus a in absolute values is less than delta, then f of x minus L is less than or equal to epsilon. So let's look at a map from x to f of x to sort of try and see what's going on here, and then we'll go more in depth with this definition. But first, the reason why I wrote it in this sort of notation instead of just saying such that for every and there exists is because people typically, once you get much later into math, you write it with these definition or symbols to make it a lot quicker and for it to flow a lot nicer. So instead of, this can all fit on one line of graphing paper of like notebook paper, but then writing out such that for every there exists, it's just extra stuff and you don't need to do that. So I wanted you guys to see the notation just so you can start to get ready for it because you'll see it a lot more later. Alright, now to the mapping. So as mapping from x to f of x, so basically you just have, it's nothing special, this is all just arbitrary, but you just have your line for x, and then your line for f of x, like two functions. So x is here, and then a is farther away. Then that maps f of a to f of x, right? But as a gets closer to f, as a gets closer to x, f of a gets a lot closer to f of x. So that's kind of what we're looking for in limits. We're trying to find it as it gets infinitesimally close, right? So it's extremely, extremely close without being the same exact thing. So, now if we wanted to look at it graphically on a 2D plane rather than just mapping, here we can see it. So we have our x and our L, right, from our equations, x minus a, absolute value is less than delta, and our f of x minus L, absolute value is less than epsilon. From there, we can get x is less than or equal to delta plus a, and x is greater than delta minus a, right? Because if you split up the absolute value, that's what you get. But you guys did that in algebra, so you should be able to do this. And then similarly, for your f of x minus L absolute value, you get f of x is less than or equal to L plus epsilon, and then f of x is greater than L minus epsilon. So you draw your bars, right? So you have your a minus delta, your a plus delta, right? Are this far from f, or x, right? They're equally spaced from x. And here are your L plus and L minus epsilon, right? So then, as you can see, it gives you this area right here, right, of this square. Which is all well and good, right? But then, as you see, as delta, let me just erase this, as delta and epsilon gets smaller, as x and a get closer together, I should say, as x and a get closer together, you get more and more lines closer to x, right? So that's shifted from here. And then this shifts in, right, as epsilon and delta are getting smaller. And then, I know it's kind of hard to see, small whiteboard, small camera, you know, but then you just get this region. And as you get closer and closer, as x gets closer and closer to a, you get the limit is equal to that, as a gets infinitesimally close to x. And that happens right here. So that's one way of looking at the precise definition of a limit. And you can see as delta and epsilon get smaller, the closer you get to the limit. So now we want to prove that limit as x approaches 3 of 4x minus 5 is equal to 7. So it needs to fill out the two equations from the definition formula. So we need x minus 3, because that's your a, right, to be less than delta. Then, from the equation, then 4x minus 5 minus 7 less than epsilon, which is the same as saying 4x minus 5, or minus 12 is less than epsilon. Oops. Right? So we want to show that when x minus 3 is less than delta, that implies that 4x minus 12 is less than epsilon. So what should we do first? Well, let's try and get this closer to this, epsilon closer to the delta. So how can we rearrange this? Well, we can rearrange it to be 4 times x minus 3, which is less than epsilon, right? Because you just take the 4 out of the absolute value, and you get x minus 3 is less than epsilon. Hey, that looks pretty good. Well, you know, we're getting close. We have x minus 3, this is x minus 3. All right, so what do we do next? Well, let's divide out the 4 on both sides, and then you have x minus 3 is less than epsilon over 4. So that implies that if delta is equal to epsilon over 4, the limit exists, right? So now, what you have to do is you have to prove it. So there's two parts of proofs. There's like the beginning phase, the sketch, where you find what you want to do, and then the second part is the proof, where you plug everything back in to show that it works. So now we're doing the proof part. So what we do is we choose delta to equal epsilon over 4, right? And then you plug it in, right? So you have your x minus 3 is less than delta, right? Which is equal to epsilon over 4, right? So then you multiply by 4, and then you have 4x minus 3 is less than epsilon, and then you distribute the 4 in, and then you get 4x minus 12 less than epsilon, right? Which is the same thing as saying 4x minus 5 minus 7, which is less than epsilon, which is what we wanted to prove. So there it is. Limit as x approaches 3 of 4x minus 5 is equal to 7, because it checks if delta is equal to epsilon over 4, then that implies epsilon is greater than 4x minus 5 minus 7. So that's pretty much all you have to do. Alright, now on to some more definitions. I know definitions are kind of just hard to look at and it's just kind of annoying to do, but you got to learn them. So I take note of these. So the definition of a left-hand limit, which is the left-hand side of like the f of x, or so if it's approaching from this side, that's the left-hand limit. So the limit as x approaches a from the left, which is the minus, of f of x equals L, if for every, upside down a, for every epsilon greater than 0 and delta greater than 0, such that a minus delta is less than x, which is less than a, then f of x minus L is less than epsilon. So it's the same thing as the precise definition of a limit, but instead it's not, you don't have the absolute values of the a minus x is less than delta. All you have is the a minus delta is less than x, right? So it doesn't have to account for both. It only accounts for one side of the limit. So now on to the right-hand limit. The limit as x approaches a plus, which is a from the right side, f of x is equal to L if for every epsilon greater than 0, delta greater than 0, such that a is less than x, which is less than a plus delta, then f of x minus L is less than epsilon. So this is the other side of the limit. Obviously, it's the right-hand side. This brings the other part of the absolute value, and so it has the right-hand side. So the limit exists if both the right-hand side and the left-hand side are the same limit. Alright, now onto the definition of an infinite limit, and that is the limit as x approaches a of f of x is equal to infinity if for every m is just a random number, for every m greater than 0, there exists a delta greater than 0 such that if x minus a is less than delta, f of x is greater than m. So pretty much what it's saying is the same thing as the beginning. X minus a has to be less than delta, and that implies that f of x is going to be huge. And it's so m is some large number, and f of x is always greater than m. So if you think of it as something, and we're going into this next lecture, but if you think of like an asymptote, like something, it's going up right here, and it goes up forever to infinity, that would be a positive infinity limit, right? Because the limit of this, since this forever goes up and doesn't hit the y-axis, it goes up forever, thus the limit is equal to infinity. So now, the definition of a negative infinite limit. Limit as x approaches a of f of x is equal to negative infinity if for every n, again, just a random n has to be less than 0, there exists delta greater than 0 such that x minus a is less than delta, same thing as before, then f of x is less than n. And these are pretty much the same exact things, except the n is a very, very negative number, a large negative number, and the m is a very large positive number. So I'm just going to use the same graph again. If you had the curve like this, and it's going down to negative infinity, this would be a negative infinite limit, because it never hits the y-axis, and therefore the limit would be equal to negative infinity. Alright, so that's all for the lecture portion of the video. Let's transition into some practice problems. Alright, now onto the questions. We're doing number 18, and maybe another one. I just know this is going to take up the whole board, so we're just doing 18 right now, and then I'll choose another one after we finish. Alright, so prove using the epsilon delta argument that the limit of as x approaches 4, 2x minus 5 is equal to 3. So what you want to start off by doing is by doing the epsilon delta inequalities. Right? So you have your less than delta x minus a 4. So x, the absolute value of x minus 4 is less than delta. Then you have 2x minus 5, because that's your f of x, minus L, which is your 3, is less than, all in absolute values is less than epsilon, right? So this is the same as saying 2x minus 8 is less than epsilon. So what can we do? Well, so we want to look at this and make it look like that, right? For the most part. That's the general idea. So what can we do? Well, we can take out a 2 here. So let's take out 2. 2 of x minus 4 is less than epsilon. Hey, x minus 4, that's great. So let's divide by 2, divide by 2, divide by 2. Then you have x minus 4 is less than epsilon over 2, right? So that's perfect. So now, what we do is the proving step, where you have to plug it back in, remember? So you can't just say, oh, epsilon, x minus 4 is less than epsilon over 2. You can't just say that. You have to do it again. So what you do is you say take delta to equal epsilon over 2, and then you plug it into the delta equation. So that is x minus 4 is less than delta, which is equal to epsilon over 2. So then you have x minus 4 is less than epsilon over 2. And now you multiply by 2, cross those out, multiply by 2, and then you can bring it into the absolute value, because this isn't going to, change the negative, you're just multiplying by a constant. So then you have 2x minus 8 is less than epsilon. And now you just, try to get your old f of x, which is the same as saying 2x minus 5 minus 3. Oh, that's an epsilon. Yikes. I'm so used to writing epsilons for my 148 class, that's all I can write even when I want to write a 3. And then have that less than epsilon. And hey, that's what we were looking for, right? 2x minus 5 minus 3, which is our L, is less than epsilon. So that's perfect. So you can prove limit that x approaches 4 of 2x minus 5 is equal to 3. Alright, not too bad, right? Alright, so now we're doing number 42. It's prove the limit as x approaches negative 3 of 1 over x plus 3 to the 4th power is equal to infinity. So what we have to do is we have to use a definition of the infinite limit, and we have to have x plus 3 is less than delta in absolute values, and then 1 over x plus 3 to the 4th is greater than m, right? So if you remember from the equation, or the definition, those are the equations we need to fill out for this to be true. So let's start with this bottom one, as we always do. Let's start at, this one is, you could call it the epsilon one. Obviously there's no epsilons, but you start with the second one, the bigger one. So 1, this is the same as saying 1 is greater than m times x plus 3 to the 4th. Right? That makes sense, right? Yes. And then, so we know delta, we see x plus 3, delta, so that means we know if we switch this with delta, right, that's delta, then it's going to be even smaller, so m delta to the 4th is still less than 1, right? So then what we want to do is we want to isolate delta now. So what we do is we have 1 is greater than m delta to the 4th, right? Then we divide by m, the 1 over m is greater than delta to the 4th, and you tetra root it, I'm not sure really what that is, do that, and then you have delta less than 1 over 4 to the m, right? So if we have our delta to be that, then this is proven. So now what we do, we plug this back into our formulas. So we have x plus 3 less than delta, right? And then, so we change delta with the 1 over square root of 4 the m, or whatever that is. So then you have x plus 3 is less than 1 over that. So now we want to get it back to this, right? So then we'll start by multiplying the quad root of m on both sides, right? So then we get 4m, and then x plus 3 1, right? So this is all looking good. It's all less than 1. Okay, now what we can do, we want the m by itself, so divide by absolute value x plus 3. Alright, divide by x plus 3. Boom. So now we have the 4th root of m, 4th root of m is equal to 1 over square root, or absolute value x plus 3. So now, let's quadruple everything. Quad it, I don't know. M is less than 1 over, and then because these are absolute values and that's to the 4th power, that will always be positive because, you know, even roots are always going to be positive, so you can get rid of the absolute values, and then you just have x plus 3 to the 4th. So then you have m is less than 1 over x plus 3 to the 4th, when you have delta equal to 1 over the 4th root of m. So that proves that the limit of x approaches -3 of 1 over x plus 3 to the 4th is equal to infinity. So that's all for lecture today, or well, and questions. Yeah, sorry I was gone for so long. I'm actually coming back to stay. This was actually really fun. I haven't filmed in a while. Had a good time. So my name's Logan. Thanks for watching. Have a great day.